I'd like to give some context regarding today's speaker, and to do that, I'd like to take us back to the year 1990, about 30 years ago. Digital image compression was about to become mainstream with the ratification of the JPEG standard. There was intense, maybe cutthroat competition in the air to dominate the format for carrying videos on compact discs. And it was in that year that I joined Hitachi America's Digital Media and Systems Laboratory, which was in Princeton, New Jersey. But there wasn't just Hitachi, there was also Matsushita and Panasonic, Mitsubishi, LG, Samsung, Sony, Philips, and virtually every major consumer electronics company in the world had set up shop within about 25 miles of Princeton, New Jersey. So why was that? Well, to be near the mothership of invention, the font of knowledge that was the David Sarnoff Research Laboratory, and today's speaker was already a leader at Sarnoff at that time. Glenn Reitmeier is widely recognized as a technology visionary and pioneer in the television industry. He's been a leader in establishing revolutionary new digital standards, including the SMPTE standards for digital video, the Grand Alliance digital HDTV system that became ATSC 1.0, and the new ATSC 3.0 standard. He's now an independent consultant, recently retired from 17 years at NBC Universal as a senior vice president for technology standards and policy. And before that, he spent 25 years in digital video research at RCA Sarnoff Labs. During the 1980s, he was instrumental in establishing the digital video sampling standard and the serial digital interface that enabled all digital television studios. And during the 1990s, Glenn led the development of the Sarnoff-Thompson-Philips NBC, kind of a petit alliance, I guess, HDTV system that pioneered the use of MPEG video compression and packet data transport. He was a leader in the HDTV Grand Alliance, and he served as a board member of ATSC, the National Association of Broadcasters, and the Open Authentication Technology Committee, the OATC, and was a chairman of both ATSC and OATC. He's a SMPTE Fellow and a recipient of the Progress Medal and the Signal Processing Medal. He's also an inaugural member of the Consumer Technology Association Academy of Digital Television Pioneers and a recipient of the NAB Television Engineering Award. Glenn holds over 60 patents and is recognized in the New Jersey Inventors Hall of Fame. Now, without further ado, we present Glenn Reitmeier.
Thank you so much. And thank you to the Princeton Computer Festival and to the College of New Jersey and the Sarnoff Museum and IEEE for your outreach and for suggesting and sponsoring this talk. For those of you who are joining us, thank you so much for your interest in this topic. And if you're a former colleague from NBC or Sarnoff, or an industry colleague from ATSC, I thank you for joining and for your support. If you're a student at TCNJ, I hope you'll get some insight into the importance of standards and the role that they play, as well as some idea of some of the core technologies that enabled analog television in earlier decades, as well as the most recent digital standard. So, and thank you also especially to Professors Katz and Perlstein for all of their help in putting together the talk and organizing the sponsorship. Thank you all so much. So by way of introduction, I'm not a technology historian, but I've become somewhat of a student of analog TV development through the years. I'm not an economist. I can observe market adoption data and trace the roots of technology, though. I'm a TV technologist. And in my early years of my career, I worked at Sarnoff on improving analog broadcasts and receivers. And in my later years at Sarnoff, I was the leader in setting digital television standards, both ATSC and ATSC3. So what I offer you tonight is sharing a technology perspective on television broadcast standards and their impact. And in particular, we're going to keep it to a US perspective. TV efforts were truly global, but we just can't even touch that aspect of it in a short talk this evening. So we're going to focus on US developments, understanding that technology race was indeed global. So I want to start off maybe just giving a little background on the importance of standards, and then we're going to talk sequentially about monochrome television, that's black and white, color television and the analog standard, digital HD TV and the ATSC1 standard, and then what we call next-gen TV, or the new ATSC3 standard. And in each one of those, I want to share a little perspective on the goals of setting a standard? What were the challenges? What were the innovations? What's some of the history? What are the core technologies? What did the adoption look like? And what was the impact of it? So fasten your seatbelts because this is going to be a quick ride. So we're going to cover a lot of material. Let's start with the importance of standards. Every manufactured item in the modern world is based on a technical standard of some kind, whether it's a simple thing as a nut and a bolt, or whether it's as complex as an airplane engine, or as complex a thing as a television standard. The world of standards is the way that we write things down and document technical designs so that parts are compatible, so that things are interchangeable, and so that systems are interoperable. Without standards, we wouldn't have the basis for the modern world that we enjoy today with all of the technology at the incredibly low costs that we have. In particular, broadcast standards specify a signal that's sent from the transmitter to receiving devices. And having a standard means that a TV station can be received by many different manufacturers' TVs. It also means that consumers can receive different TV stations all on their single TV. Regardless of what the channel is, the technical standard is the same. And that technical standard has oversight of the Federal Communications Commission, which is responsible for policing the airwaves and making sure that they're efficiently used to serve the public. And we'll talk more about the role of government and regulation as we look at their role in different standards over the decades. So let's start off by talking about black and white television, monochrome TV. I think David Sarnoff articulated the goal so very well during one of the first televised events at the 1939 World's Fair, which was to add sight to sound. And I think historically, we have to remember that as television was being developed, radio was pretty mainstream. Most households in America in the 1930s had a radio or had access to a neighbor who had a radio. And radio was a new mass medium that had been created in no large part through the effort of RCA, but with other companies participating in the industry as well. Now, if you thought about adding sight to sound in an era of analog circuits, and indeed not just analog circuits, vacuum tubes, it was a pretty daunting kind of thing. Look at the picture of the typical tube radio in the 1930s. I mean, we had a small handful of tubes and a power supply and a speaker. And against that kind of technology backdrop, we had to add sight, which had 280 times more information than a radio signal. We had to put that into 200 times more radio spectrum than was used for a radio signal, sorry. And we had to design high power transmitters and high antennas to get it to the home. People had to put up a rooftop receive antenna, and it was a huge challenge for the industry to design affordable receivers that would enable people to afford a television and to bring this new technology of remote vision into their home. And to boot, there were multiple systems under development and proposed here in the US, as well as in other countries throughout the world. Well, by 1936, the industry thought they had it all figured out. And the Radio Manufacturers Association set some industry standards and proposed to the FCC that US television channels should be standardized. And we need a 6 megahertz bandwidth. And we'll deliver 441 lines interlaced with 2.8 megahertz of visual bandwidth. Now that's a pretty low resolution picture. And you look at the old 1939 RCA receiver there, pretty low resolution picture was appropriate for a display that size. It probably not much bigger than a small laptop display. That's probably a 9-inch display or so. Well, anyway, the industry thought they had it all figured out. And the FCC said, well, I think you can do a little better. They said, actually, it's not good enough. And so committees were formed, compromises were made, And the industry worked together in the National Television Systems Committee to come up with a system that did work in 6 megahertz bandwidth, but it used some very, very clever analog tricks to get higher resolution in that 6 megahertz to deliver 525 lines of picture. And they actually used FM audio too, which is much higher quality than the AM audio that was originally proposed. Now, there were great debates about the benefit of increased horizontal resolution versus the number of scan lines, but a compromise was found in the 525 line system that was in service for over 5 decades here in the US. Now, monochrome television is based on a lot of really clever technology and a lot of technical innovation, again, considering the time and the era of the technology being vacuum tube based. In the early days, everything was based on the idea of a cathode ray tube, which deflects an electron beam across the face of the cathode ray tube, and the brightness of the spot and the location are the things that are controlled by the details of the signal that's broadcast. So on the top of the picture, you'll see an example television waveform that carefully controlled sort of the zigzag pattern by which the electron beam scanned the face of the cathode ray tube display. And we literally painted a picture on that display, spot by spot, left to right, top to bottom. And then we used a clever trick that said, you know what? I'm not going to go back to the exact same spot again. I'm going to drop it down a little bit, and I'm going to paint lines in between the lines that I just painted. And that particular innovation was extremely important to avoid display flicker on a CRT in those days, because the flicker was all about the decay of a phosphor that was on the plate. So a tremendous amount of cleverness and designing a signal that was all intended to drive the only viable display technology at the time to actually trace out a picture and make a picture on the screen. So quite incredible. So here's some more details about what a black and white TV signal really looked like. If we make the picture on the top left there, the staircase of brightness from white to black, that's represented by the signal that's shown on the top left. And we see that the voltage of the signal, if you will, represents the brightness on the display. And in sort of the middle of the picture, you'll see the white bar, and then it steps down gradually. Now, that negative going pulse on the left-hand side was the pulse that very cleverly retraced the CRT beam from the right side to the left side of the picture. So that was designed into the waveform in a way that was extremely clever. The other thing that they did technology-wise was they found a way to be more spectrum efficient by being half single sideband and half double sideband, a technique that they called vestigial sideband. And what that allowed was higher resolution in the transmitted signal without using both sidebands of the radio frequency spectrum. So they literally got 4.2 megahertz worth of visual bandwidth in 6 megahertz of RF spectrum, and did it in a way that it was very cost effective to design a receiver with tube circuits to decode that signal and actually make the display. They did other clever things too, like they realized that the signal was white a lot of the time, so they inverted the radio frequency signal for power efficiency. The peak transmission power only occurred at the tip of those synchronization pulses. Most of the time, when the picture was gray or white, the transmitter was actually lower power. So that is a very, very brief introduction to the very, very clever and innovative designs that formed the basis of the technology for black and white television. Now, as I said, in 1942, the standard was set for black and white television. Of course, this was right at the beginning of World War II, too, which of course disrupted the adoption of television. But the industry got busy designing receivers and television cameras and antennas and putting up broadcast antenna masts. There's the top of the Empire State Building. And the industry stepped up to building that technology and investing in it, even though there were zero receivers out there. It was all about seeding the marketplace. Now, one of the artifacts of analog transmission is that very cleverly designed signal that I showed you is susceptible to things that happen to it during its over-the-air transmission. As the signal gets weaker, it gets noisy compared to the level of background noise in the atmosphere or in the ether, right? So the signal gets snowy or fuzzy as it goes toward the receiver. It's also susceptible to what we called ghosting, which is a reflection from another object. So a mountain can cause a reflection, so can a building. And there can also be interference from other television stations that are geographically located nearby. So the FCC had to carefully regulate the power that was allowed for a TV transmission and the location of different stations in order to create an orderly ecosystem that would allow for good reception and would be prone to good quality signals available to consumers, and where everybody hoped that they would adopt the new television standard and buy receivers. Now, consumer adoption is quite interesting. As I mentioned, of course, World War II interfered with the adoption of color television. But this chart from the Consumer Technology Association plots the number of TV sets that were adopted and out there in the marketplace versus the price of a TV set. And of course, as you can see, in the years between 1954 and the mid-1960s, black and white television adoption started to go up, pretty dramatically, especially as the price fell. And indeed, television was a novel new thing for America and became a powerful new medium, that started to supplant radio, in fact, right? And that leads us to a story about color television. Now, as we saw from the previous slide, I'm going to go back for a minute. You can see that the black and white adoption curve on the top starts to decline in the middle 1960s. But that's because color television came along in a compatible way and kind of became another wave of adoption. So let's talk about color television and how that worked. The whole goal of color was to add the color part of the signal in a backward compatible manner, so that one signal would make the bar display on the left for a black and white receiver, but would make a color display, as you see on the right, for a color TV receiver. And that was a huge technology hurdle to ask for from technology as well as standards. So what were the technology challenges? Well, we had to find a way to get 3 times more information than monochrome TV. In order to make a color picture, you need a red, a green, and a blue signal. And those combined make the different combinations of colors. It had to fit in the same radio spectrum, 6 megahertz, had to be backward compatible with monochrome TV receivers. And once again, multiple systems were proposed. Now, actually, in the early 1950s, CBS came up with a clever design that sequentially sent red, green, and blue pictures. And the display was based on the idea of a rotating color wheel. So there was a monochrome CRT behind that color wheel that rotated, and they would flash a red picture and then a green one and then a blue one and so on, just to sequentially create the color. Now, the Federal Communications System said, that's great, we'll approve that. We finally have color TV. And RCA, and David Sarnoff in particular, kept up the pressure to develop an all-electronic television system. And indeed, in 1953, an all-electronic color standard was developed, largely led by RCA and many innovations occurring at Sarnoff Labs in Princeton. But to the extent that the FCC eventually repealed their approval of the color wheel system in favor of the 1953 NTSC color standard. So a remarkable misstep and then a reversal of government policy in terms of the standard. Now, again, let's talk about some of the technology and innovations in color television. The whole idea of color, again, we need red, green, and blue information in order to make a color picture. And one of the key developments and innovations was the idea that you could make that kind of display using a single cathode ray tube. There was a special invention called a shadow mask, which you can see on the right. It kind of let the electron beams through to hit phosphors that were laid down in a very precise pattern on the face of the tube in order to get those combinations of red, green, and blue colors. Now, in order to get a compatible signal, they actually used very important principles of human vision and color perception. And in fact, those same principles continue to serve us today, even in the advent of digital systems, which I find absolutely fascinating. And it's why I wanted to talk about monochrome and color TV, because so many of the basics of what we know as modern digital television actually have their roots in the old analog technology. Now, the actual perceptual principle is that your eye has lower resolution in color than it does in black and white. Now, the engineers understood that most of the black and white color actually came from the green signal. So they found a very clever way to transform red, green, and blue signals into a signal called luminance, which was the mimic of the black and white signal, as well as red minus the luminance and blue minus the luminance. So obviously, if you add the luminance to R minus Y, you get red. And if you add the luminance to B minus Y, you get blue. And if you have luminance in red and blue, you can get green. So you recover the red, green, and blue. But anyway, human perception allows the color difference signals, R minus Y and B minus Y, to have much lower bandwidth, at least a quarter of the bandwidth as the luminance signal, and yet the pictures still look sharp. So it was just extremely clever. The way they did the compatible signal was that they superimposed it as what they called a color subcarrier. So the subcarrier you see on the top picture there, the black and white color staircase, and on the bottom you see that superimposed on that staircase is a sinusoidal carrier. And basically, the amplitude of that carrier determined the amount of saturation, or how deep the color was. The phase of the carrier represented the hue. It could be red, could be green, could be blue, whatever. But the saturation and hue together determine the amount of color that's painted on the screen. Now, in order to be able to use the phase as a means of modulation, you actually had to have a reference. And so they also found a way to stick in this little color burst phase reference shown on the bottom, right after that synchronization pulse, in order to be a phase reference for decoding the phase of that sinusoidal carrier. It was incredibly innovative and incredibly clever. One thing they did, though, was that in order to not interfere with audio on some of the old legacy receivers, they shifted the picture rate by 1 part in 1,000 over 1,001. And that's actually why we have 59.94 hertz systems today, because of that historical shift that was made in order to not have some audio interference in some legacy receivers back then. And that plagues a lot of people, but it's, oh my gosh, for editing, for ad insertion, for all kinds of things, this non-integer frame rate is a real hassle. But think back to the day in which it was invented, and tape recording had not yet been invented. There was no way to even record a signal. Everything was live. And so, the technology at the time was an incredibly clever decision. Today, it's one that kind of, we kind of maybe regret. But nevertheless, that is what happened in the standard. Well, color TV adoption, grew after its introduction. It was incredibly expensive at first, and color TV became adopted, and it became lower and lower cost and higher quality receivers over several decades. I want to talk about the cost a little bit because it starts to come into play. Black and white TV was expensive when it was introduced, but compared to a black and white TV, a color TV was really expensive. And in fact, in 1954, a color TV was the equivalent cost of a brand new Chevrolet. Now, by 1966, a little over a decade later, 12 years later, the price of a new TV had dropped to about $2,600. That was in $1999 because at the time I was comparing to digital HD TV. So it was quite a bit less than the cost of a new Chevrolet. And color TV was incredibly appealing. And here's what happened in terms of color TV and consumer adoption. If you look at the chart, you can see that they didn't even start counting until 1966, which was some 13 years after the NTSC standard. But look at the price. As the price drops, the adoption skyrockets to the point where in the mid 90s, it was just leveling off because people had 3 TV sets in a home, and many people 4. In fact, at one point in the 1990s, I kind of have a fond memory of hearing a statistic that said that there were more TV households than there were households with indoor plumbing. Yes, that's what I claim to her, as amazing it is. So color TV took a long time to adopt because it took a long time to bring that price point down. And if you think about it, basically from 1966 to 1996, the period of the chart shown here, that's a 30-year adoption. That was a long time, and it was a long continuing struggle of ongoing innovation in receivers and cost reduction in receivers that just led to that step-by-step adoption. And we're going to compare HD TV adoption to that. So just kind of keep that 3 decades number in your mind. Now, I think when you look back at color television, and I'm kind of including black and white television in here, to me, television changed the world. It just totally revolutionized our ability to see events in real time. And many subsequent innovations were built up on the existence of that color television standard. Now, I was actually a preteen, and it was incredibly struck by seeing the first global broadcast via satellite, which happened to be the Beatles in 1967. And if you think about it, the advent of global connectivity through satellites and our ability to see events around the world in real time, and not just hear them like we did in radio, but to see them and to have that visual impact, I think that was truly nothing short of revolutionary in terms of its societal impact on the entire world. But to the more technical innovations, TV capacity was expanded through the addition of ultra-high frequency broadcasting. Cable television came about. All of cable television was built on the color television broadcast standards. They literally just lined them up in a different frequency arrangement on the cable, but the advent of hundreds of channels of programming that started to explode and change the world again in the 1980s was a direct consequence of the technology and standardization of color television. And then, of course, in the early 1980s, we have the video cassette recorder. It not only opened up a market for home recording, but it completely created a whole new market for video entertainment content and rentals and purchases. You could rent a tape, you could buy a tape of a movie. It was a renaissance for Hollywood because you didn't have to go to the theater to see a movie anymore. And you didn't have to see it at the time it was out. You could see a movie that was out of the theatrical window, and Hollywood could make money on that and consumers could enjoy it. And then there's camcording. Again, the advent of the early VHS camcorders was all based on NTSC color television broadcast standards and the innovations that led that to a recording standard for VCRs as well. I couldn't even come close to telling you I'm going to guess it's hundreds of billions, maybe trillions of dollars of economic impact that was the outcome and windfall of the NTSC color television standard. And that economic windfall spanned decades, and it spanned incredible other technology innovations that built on the shoulders of the original NTSC color television standard. Well, with that, let's go to the 1990s and that time that Larry described and what led to what we all enjoy in our homes today, which is digital high definition television and the ATSC standard. The goals of high definition television were, once again, to really improve the consumer experience and the reality of the picture and sound that people enjoyed in the home. The goals were to get at least 2 times the horizontal resolution and 2 times the vertical resolution of the traditional color television picture. Now, in addition, the industry wanted to have a wide, more movie-like 16:9 aspect ratio. And they wanted to do better than just the stereo sound that had been added to color television in 1986, actually. But they wanted to do better. They wanted to do theater quality surround sound with the best technology that was available at the time. And again, in HDTV, there's 2 commonly used formats. There's a 1080 line format and a 720 line format. And on the right there, you can see a little comparison of standard definition versus high definition. And you can see the additional resolution of the picture. But what I want you to think about is the additional resolution would have been noticeable on a 32-inch display, which was the biggest CRT display at the time. But without that additional resolution, the pictures would just look terrible on any kind of large screen display like we enjoy today. And we're going to talk a little bit later, but it turned out that I think high definition television and flat screen display technologies were incredibly synergistic, and they just created a perfect storm of adoption that led to the high resolution sharp pictures and huge, big, flat, bright, beautiful displays that we all enjoy in our homes today. Well, HDTV was quite a technology race, and this one I can talk about firsthand. In the 1980s, high definition television became quite a topic of worldwide research and development. Certainly anybody in the consumer electronics and broadcast industries realized that there was going to be a new wave of technology and that it was going to revolutionize the industry. And so how it happened and the underlying technology were extremely important. I should also mention, by the way, that the underlying technology and patents were an incredible source of profit. So the patent holders in systems that won the day in terms of being established as standards were quite an important profit contributor for the companies that invested in the research and development to develop television systems. Well, anyway, in the 1980s was a worldwide race, and many systems had been developed in Europe and Japan. By 1987, U.S. broadcasters petitioned the FCC and said, there's a high definition television wave of technology that's going to happen. Please make sure that we can participate in this. Save us some spectrum for HDTV broadcasting. Now, in response, the FCC formed an advisory committee on advanced television, and they began to entertain proposals for advanced television systems, as they were called at the time, because there were many, many different competing ideas and proposals. Some of them were, well, color TV is pretty good. We just need to do a little bit better on the resolution and crisping it up, and we'll call that improved definition. And other people said, well, we need to do a little bit better than that. We need to kind of have extended definition, and maybe we can sort of get 50% improvement or so in the horizontal resolution, and that'll help a lot. And other people said, no, we don't know how to get HDTV in a single channel, but we've got some really clever technologies that would let us get HDTV again 4 times the resolution. We'll need 4 channels to broadcast it, but maybe we need 2 channels to get HDTV. And so, okay, FCC, just allocate broadcasters an extra channel. Well, by the late 1980s, there were 23 competing analog systems with different ideas about what the next generation of television should be. Well, another false start. The FCC, to their credit, clarified the policy goals that they wanted. They said, you know what, these extended improved definition things, that's all nice, but you know what? We want full HD TV, nothing short of it. Guess what? We need it in one 6 megahertz transmission channel, the same amount of frequency spectrum that you have for your color TV. You got to figure out how to get high definition TV into that same 6 megahertz transmission channel. Because you know what? There's no additional spectrum. We're not going to allocate more spectrum for TV broadcasting and give everybody 2 channels in order to do HD TV. That's just not in the cards. And so what happened? Well, lo and behold, there were 4 digital systems that were, I'll call them skunks works, really secret R&D projects, extremely advanced, that emerged from the woodwork. And from 4 different consortiums who are backing those systems. And, as Larry very kindly said in the introduction, I was privileged to be leading one of those development teams at Sarnoff, and advocating and designing what was called Advanced Digital HD TV, which is a strong precursor to the standard that we have today. And let me talk a little bit more about the digital systems and some of the challenges of that technology race. Yeah, that's actually me in 1993. And this was when we installed the HDTV system up at NBC to do some recording trials and some broadcasting trials. And you notice on the top one of those racks on the right-hand side is a state-of-the-art color TV from the era. And just the thought that get all that digital equipment into practical TV was quite a challenge. Anyway, as I said, we had 4 competing systems in the early 1990s. By 1992, we had system testing and demonstrations that were under the oversight of the Advisory Committee and the FCC. And in January of 1993, the Advisory Committee met to pick a winner. They were bound to determine that they were going to pick a winning system and set as a standard and move on. Well, they were able to see from all the test results that a digital system was the way to go, but they were unable to select a winner from the 4 digital systems. So that set up a situation where the poor proponents of the digital systems were either going to have to figure out how to somebody get better and leapfrog the others in a way that nobody knew how to do, or we're going to have to figure out how to work together. So in May of 1993, we formed a joint collaboration called the Digital HDTV Grand Alliance. And our goal was to design a single HDTV system with digital technology that had the best attributes of each of the 4 digital systems. So it was the best of the best. And there were a lot of skeptics that said, well, first of all, how can any one system be better than every aspect of the best of all the preceding ones? Because there's always compromises and trade-offs. So there's no way you're going to get a single thing that's the best of the best. Oh, by the way, you got 4 competing consortiums who just spent the last 3 years telling the world why their system was the best and the other team's HDTV systems weren't so good, and they're going to work together and collaborate. Yeah, sure. Well, it actually happened, and we did pull it off, and thanks to just tremendous selflessness and dedication of my colleagues at Sarnoff and all the Grand Alliance companies, AT&T, Zenith, General Instrument, Phillips, Thomson, and Sarnoff. In April 1995, we unveiled digital HD TV to the world, and it was the world premiere. That happens to be me in 1995 doing a demonstration of the HDTV system for FCC Chairman Reed Hundt at the time, which all led to testing, rigorous testing of the Grand Alliance system. It did indeed meet the best of the best criteria. It was documented and standardized by the Advanced Television Systems Committee in September of 1995. And after some political turmoil in 1996, it was indeed approved by the FCC on December 24th, 1996. And it was the world's very first digital television standard. Let's talk about, again, let's revisit some of the technology challenges. We needed to have 5 times more information than conventional TV. We had limited spectrum capability. We had transmissions that can't interfere with legacy service. We had to have robustness to survive interference. And maybe most significantly, we had to find a way to have receivers that were affordable so that the industry and consumers could adopt them. In the era of analog television in the early 1990s, again, you have to sort of put it, it was so revolutionary because you have to put it in context. Computers were DOS. They were Windows 3.1. Modems were 19.2 kilobits dial-up. VCRs were analog and cell phones were analog. So HDTV was a million times the number of colors in a computer display. It was 1,000 times faster than a dial-up modem. It was compressed digital video in an era of analog recording, and it was digital transmission in an era of analog cell phones. So it was indeed incredibly revolutionary. The ATSC standard is built on the idea of a layered digital system. It has high definition and standard definition systems. It uses digital and audio, video and audio compression. We put data into flexible packets with headers that tell what kind of data it is. And we have a robust way of sending the bits over the air. I'm going to fly through some of these because we're running out of time. The challenge of digital video is you need to send a picture in 2% of its original data. Now, how do you do that? Again, Larry in the introduction said how JPEG was just coming into the forefront. And we're familiar with JPEG pictures on our cameras. And we break a picture in little blocks. And each one of the little blocks, we do mathematical operation on it in order to be able to approximate the waveform with a few coefficients. And because this is a technology credit course, here's the equation, okay? TCNJ students, I want you to look at this equation. This is the computation of this discrete cosine transform. So you can say you saw an equation in this talk. So like JPEG, that's one of the basic parts of digital video compression. But the other one is that video is a sequence of frames. In an analog TV, we send every frame, every time period. So we repeat a lot of information. In digital TV, what we do is we predict the frame from the previous frame, and we say, well, we're almost right, but here's some correction data. So we compute vectors for each block and allow the previous frame to be a predictor of the current frame. And then we send data that says, okay, here's the little bits that are wrong about that. And so it's kind of the edge information that you see in the graphic icons here. And so in digital systems, we send frames that are composed of prediction data and correction data. And we put that all together with JPEG. And in fact, we use those pixel blocks and the discrete cosine transform for all the frames, whether they're individually coded or whether they're coded as a predicted frame and corrections. As I said, we organize data into packets, and that's entirely new. In fact, it was revolutionary because in analog television, one program occupied a whole channel. In digital television, we were no longer confined to having one program and one channel. In fact, the idea that we had data and data packets was fundamentally revolutionary because we could have an arbitrary number of channels of programming in a digital television channel. Could have one HD TV or 5 standard definitions or one HDTV and a couple of standard definitions. And in fact, all of those combinations are commercially used today. In digital transmission, it's kind of an all or nothing proposition. If you get the bits, the picture is going to be perfect. And if you don't get the bits, you're not going to get anything. So it was, again, a game changer in terms of the picture quality that people receive. No more jiggling around the antenna and is this picture good from this station? Is that picture good from that station? You kind of either got it or you didn't. So, and here's an actual example of the ghosting and noise that was seen on a typical analog signal shown at the top. Again, susceptible to all those impairments in the over-the-air transmission. And the digital signal, if you got it, it was perfect and it was stunning high definition. The FCC mandated a transition to high definition. They said, gee, if you're in the top 10 television markets, you're going to be on air by sort of 2002. And if you're in the next 30 markets, you're going to be on air a few years later. And at the same time, they established requirements for digital television tuners to be built into receivers. So they took a very policy-centric and heavy government hand in mandating the transition to high-definition television. The original plan was to start the transition in 1998 and to be completed in 2006. In fact, it took till July of 2009. But when you talk about a change, the order of magnitude of changing out every television set in America, and again, compared to the adoption of color television over 3 decades, the accomplishment of going from analog technology still in 1998 to a fully completed digital transition just 11 years later in 2009 is absolutely stunning. So, kudos to all the broadcaster and consumer electronics, and government leadership that enabled that rapid transition to digital HDTV. And speaking of that adoption, in 1998, when HDTVs launched, they were under $9,000, which was a lot less than the cost of a Chevrolet in 1998. And here's what HDTV adoption looks like compared to color television and VCRs. As you can see, it's significantly faster than PCs, much, much faster than the decades that it took color television. So it's a real success story of technology being revolutionary, as well as industry and government leadership. Now, as far as the impact of digital HDTV, I think it's been absolutely profound. If we didn't have digital over-the-air HDTV, we wouldn't have digital cinema. We wouldn't have had digital cable or digital video discs. It directly enabled satellite pay TV systems to compete with cable and to be available to rural America. Because of digital cable, the cable industry innovated cable modems. Because of DVD and Blu-ray, the movie industry innovated with digital downloads. And if you look at the combined advances in video compression and cable modems, those are the 2 things that contributed to our modern ecosystem of video streaming over the internet. So we wouldn't have broadband internet access if it weren't for digital cable, if it weren't for ATSC, and we sure wouldn't have streaming content if it weren't for digital high definition TV. So I know myself and my colleagues in the Grand Alliance are extremely humbled and proud of the impact that our efforts have had, not just on broadcasting and not just in the US, but on television technology throughout the world. But let's talk about the future and what's happened since ATSC 1. We're going to talk about next gen TV and ATSC 3.0. By the mid-2000s, it was starting to be obvious that technology of the early 90s was starting to get supplanted. We had cable modems, we have laptop computers, we have wearables. By 2007, we had iPhones. iPhones were launched, mid-2000s. And we started to have smart flat panel TVs. So it was obvious that there were rapid advances and ongoing disruptions, and that those were going to outpace the ATSC digital HDTV standard that we had just finished transitioning to. We're in the middle of it at the time, but actually it was important to see that the change was coming once again. And so at that point in time, I was chairman of the ATSC, and I challenged all of our colleagues to step up and rally together. And we did. And ATSC came together and said, yes, we're going to be out in front, and we're going to design a next generation digital system so that it's ready when it's really needed in the marketplace. We want to deliver not just picture and sound. We want a modern app experience with personalization and interactivity. We need ultra high definition 4K resolution, and we need high dynamic range pictures. We need to do better than 5.1 surround sound. We want to do immersive audio. And by the way, we want to interoperate with internet protocol based devices that are now proliferating through consumer households. You know, your tablet, your phone, your PC, they all speak internet protocol. And by the way, wouldn't it be amazing if broadcasting could integrate with that and be part of the internet as well? And we wanted new flexibilities in data transmission and robustness, the ability to insert targeted ads. And of course, once again, we needed to have affordable receivers. So I'm proud to say that the ATSC began the next gen standardization effort in 2012. And by 2017, the standard was completed enough that it was actually approved for voluntary use by the FCC. Technology challenges. Well, 4 times more information again. But by the way, another 25% more information to do high dynamic range video. I'm going to talk about that in a minute, but blacker blacks, whiter whites, more vibrant colors. 4 times more information in audio, and new needs for transmission robustness and to be able to reach mobile receivers. But by the way, this time around, we're not going to have the competitive multiple system proposals. We're just going to hammer it out in a collaborative industry process. And again, I'm really, really proud to say that that's indeed what happened in ATSC. So the idea of a broadcaster app today, the statistics, the logos, all the things that you see are a common experience. It's all burned in at the TV station. Well, modern systems don't do that. In fact, ATSC3 uses the same HTML5 technology that's used in today's internet browsers to be able to personalize and customize the overlays that you see on the screen. Following a particular player, want to see their stats? No problem. Following a particular team, you want to hear their announcer as opposed to the sort of generic announcer. You want to hear that team announcer? No problem. You can have a customized, individualized audio track as well. Picture and sound, again, more vivid, higher resolution kinds of pictures and immersive audio. Here's some more about that. 4 times the resolution of HD TV, astoundingly, but you need that kind of resolution when you start to talk about 65-inch flat panel displays like we commonly have today in 4K ultra high definition resolution. High dynamic range, blacker blacks, whiter whites. Finally getting away from the CRT nonlinearity that defined television since black and white, defining a new technique of mapping the signal brightness onto the actual display called perceptual quantization. And those options are now available to broadcasters in ATSC3. Immersive audio, sound doesn't come from 5 places. It comes from anywhere in a sphere around you. And it's coded not just as channels, but as objects. So amazing advances. Same basic concepts in terms of video and audio compression. We break pictures down into blocks, except now, in order to be so much more efficient, we're just incredibly sophisticated about the size and shape of blocks that we use for motion prediction and to send those corrections. So as opposed to fixed size blocks like are used in JPEG, we have adaptive block sizes that are all computed and determined to be what's best breakup of blocks to actually code and compress an individual frame of video. As I said, IP was so important because it makes broadcasting part of the internet. We want broadcasts to be able to seamlessly reach home devices. And that's just a really important feature of ATSC3. In fact, I would say it was a design principle of ATSC3. In ATSC1, we had one kind of bits. You got them or you didn't. But in ATSC3, we have the capability to send different bits with different robustnesses and to actually send more than one stream of data in a signal. We use a whole new technique of modulation, which actually uses thousands of different carriers, each one carrying different kind of bits. And we literally have a knob that we can turn on robustness versus data capacity. So a huge first in terms of a digital system. So here you see that in one channel, we could be sending a low data rate that's super robust, and then a little higher data rate with high robustness, and a very high data rate with kind of the normal level of transmission robustness. So broadcasters can configure a signal for different services that consider geography, terrain, receivability factors, and what's the kind of data that I'm sending. Can be audio, can be video, can be data files, or any kind of bits. Sophisticated ways of superimposing signals on themselves actually give even more flexibility in broadcast. And we can use those robust bits to actually send a low resolution picture and then incrementally a higher level of picture, that being called spatial scalability. And here in this picture, you kind of see the lower resolution, in this case meaning standard definition. You kind of see that as a base layer with the idea that you can send the additional edge information as an enhancement layer. And you can send those with different levels of robustness. And that's all intended for, I can send the robust layer for indoor reception or for automotive reception, and still deliver really good pictures for screens that are those sizes, while at the same time using the enhancement to deliver ultra high definition to large screens that are, static and in people's family room. The voluntary transition that was allowed by the FCC is a tricky one for broadcasters. They need to figure out how to share channels and share spectrum in order to create the capacity of a new station place in the market. And so that's a bit of a tricky process, but I'm proud to say that broadcasters are stepping up to the plate and are learning how to collaborate. And so the column on the sort of mid-left there shows the idea that by putting 4 channels worth of information onto 3 existing channels, we can create capacity for a new ATSC3 signal on station B, and therefore have both ATSC1 and ATSC3 transmissions simultaneously in that television market. Rollout's going amazingly well. There's already 60 television stations up and running in 16 markets, and TV receivers are being introduced this year. Actually, over 20 models announced at the Consumer Electronics Show. So I predict this one goes even faster than ATSC1. One other thing that we did for future was the actual signal is not just OFDM. There's actually a mechanism called a bootstrap that says, we're going to tell you what the signal is for a coming period of time, a certain number of milliseconds. And when you hear this, so when you hear this tone, what's coming next is an OFDM signal. But by doing that, we actually leave room for future unknown signal types so that the technology of broadcast television can evolve in place through time slicing of the broadcast frequency spectrum. So I think quite an important nod to being able to evolve the future of television in place. I see that we're coming up on an hour. I'm going to go very quickly through some future predictions. As I mentioned, there's 20 TV models launching in 2020, and that's extremely rewarding. And a big part of ATSC3 is that by being internet protocol based and by leveraging standards that are already used in video streaming over the internet, those TV receivers are already very affordable and very manufacturable. Here's just an example of, compared to that ATSC1 prototype that you saw with all those racks and me standing in front of it, an ATSC3 receiver today is already a tiny dongle or a small circuit board with a single silicon system on a chip IC. And so based on that, I can predict that just based on the cost being almost nothing to add ATSC3 capability to an already smart TV receiver that's internet connected, I predict that adoption will go really fast. Well, we have the internet. Who cares about broadcasting? Well, about 20% of Americans do. Did you know that pay TV households are shrinking while over-the-air antenna use is actually growing? There's over 17 million antenna-only households and another 4 to 5 million antennas in pay TV homes. Over-the-top internet and over-the-air is a growing combination. Again, and just perspective on that, the largest pay TV operator in the country is Comcast, who has about 22 million subscribers. And together, the over-the-air households in the United States are about 20 million. So, comparatively wise, the number of over-the-air TV households is about the same as the largest pay TV operator in the country. I mentioned the importance of IP, and I think it'll unleash some really interesting innovation in terms of consumer products. The idea is that you can have a home gateway that receives the over-the-air signal, but redistributes that signal anywhere in the house using Wi-Fi. And of course, Wi-Fi is spoken by your smart TV, by network attached storage, by your phone, by your tablet, by your PC. And so the idea is that you don't have to have an antenna on every device. You have to have an antenna one place in the house. And then having a home TV gateway will facilitate seeing that broadcast content on any device. And finally, I'm just going to close with the idea that next-gen TV, which again is commercial name for ATSC3 standard. Next-gen TV is a platform. Of course, the core services that broadcasters are going to launch with and are going to deliver are all about the continuation of their television broadcasting business. But ATSC3, next-gen TV services, they can be zoned, they can be hyper-local. We can deal with weather emergencies and distance learning and agriculture. We can broadcast bits to tractors and buildings and to cars and the notebooks and tablets and ebooks and any other device that you can think of that can speak IP. We can find a way to get a broadcast signal to. And so the idea that broadcasting economically delivers bits to millions of devices at once that need those bits, I think is an incredibly powerful addition to the internet applications that we have today, where we individually deliver bits to every device. But the power of one-to-many and the power of broadcasting, I think, is going to be a revolutionary capability for broadcasters, but also a valuable addition to the internet that we enjoy today. And with that, my gosh, it's been a whirlwind tour from monochrome TV to color TV and low-resolution pictures to digital HDTV that we all have in our homes today, and to the advent of next-gen TV and ultra-high definition and a newly flexible internet-based broadcast platform. It's been an incredibly wild ride of technology over more than 8 decades. And for me, it's been a privilege and a pleasure to be a part of the digital revolution. And again, a big thank you to the many colleagues that I've worked with over my career and colleagues from the Grand Alliance and ATSC who were so much a part of those technical advances and innovations. And I thank you all for joining us. Here's some more information in terms of books and technical papers and websites. If you want a real deep dive on ATSC3 technically, the Society of Motion Picture and Television Engineers has a virtual course that I participated in giving. So if you want a real deep dive, take a look there. But I thank you. That was a whirlwind ride. I know I spoke quickly too. If you have any questions, I'll be happy to take them. But I want to thank you all so much for tuning in and for your interest in sticking with me through this crazy whirlwind tour of technology, challenges, impact, and adoption. Thank you so much.